Today we are going to be talking about the frequency response of linear systems. So I'm going to re-go over some of the stuff that we addressed right before the test because I feel like I did a poor job of it, and hopefully I can do a slightly better job today. So what we're doing here is we are making a pretty considerable shift in how we are choosing to look at our circuits. Okay. So what I mean by that very specifically is up until this point in this class, what we have been doing is using the Laplace transform to analyze our circuit in the S domain and then go back into the time domain to understand how our system behaves as a function of time. Frequency response, if you guys recall from circuits 2, is a representation of how our circuit or system behaves as a function of frequency. Okay, and so we're going to be doing this in the S domain. Now, one of the big reasons why I was unsatisfied with what I showed you guys the previous day is because of how important this topic is. So we're going to introduce you to some concepts here in circuits 3 that you will revisit in many other of your upper level classes. So you'll get a little bit more detail when you take linear systems and signals next quarter in electrical engineering 321. You are going to be applying a lot of this stuff in electrical engineering 336. So as these techniques apply to transistor amplifier circuits when you take electronics 2. And what we're doing in here is a fundamental building block of what you're going to learn in your control theory classes, should you choose to take that as a senior option, or your communication classes, should you choose to take that as a senior option. So this stuff is going to pop up literally everywhere as you progress throughout the remainder of your electrical engineering degree. So, an important way to describe the frequency response of a network or system is through its transfer function, H of S. So let's call this part, why is this doing this thing where it's writing all shiddly again? Hold on. Now I'm annoyed. Save it, close it. Okay. So let's talk about, it's doing it again. Transfer functions. Poles and zeros. I'm really sorry. I don't know why it's being ridiculously sensitive. So if you have any questions about what any of this stuff is supposed to say, please ask. I don't know why my stylus is acting up. So transfer functions can be a couple of different things, okay? So, and it depends on the type of system that we are interested in. So you may recall from circuits 2, probably on the first or second day of class, in circuits 2, we talked about the different type of amplifier circuits. So we had like voltage amplifiers where we had voltage at the input, measured voltage at the output. So we had a voltage amplifier. Current amplifier was, we put a current on at the input, we measure a current at the output. Trans impedance amplifier was, we put a current at the input, we measure a voltage at the output. And then transconductance amplifiers was, we put a voltage at the input, measure a current at the output. So we're going to have a different transfer function for each of those types of systems, okay? So we could have an H of S that is the ratio of V out as a function of S to Vn as a function of S. And we would call this the voltage gain or the voltage transfer function. Let me see if I have another stylus. Does it connect through Bluetooth?
No, it's not Bluetooth at all.
Right. Swear to God, my new stylus only breaks when I'm in this class. It works perfectly fine in circuits 1 every damn morning. So I don't know. All right, so we've got a voltage transfer function that is just the ratio of the output voltage to the input voltage. We could also have a current transfer function that would be the ratio of I out as a function of S to I in as a function of S. So this would be our current gain. We could have an H of S that is V out over I in. So this would be a trans impedance gain. Or we could have an H of S that is I out of S over Vn. And this would be a transconductance gain. Okay. So these transfer functions are extremely useful because they provide a way of describing the output of the network due to any input. So they are playing the role of the impulse response H of t, but in the S domain. So they're letting us know what's going on as a function of frequency, whereas H of t let us know what's going on as a function of time. And that's literally the reason why we use capital H for our transfer functions, because it is just the Laplace transform of H of t, the unit impulse response. Okay. So I want to look at a circuit. Okay. Yay, my stylus stopped being a douche. So the circuit that we're going to look at and determine its transfer function of is something that's fairly simplistic. Okay. So we have some time domain input signal Vn of t. And I'm going to put some resistor R1 here in series. I'm going to put some inductance L here. Some capacitance C here. Some resistance R2 here. And we are going to define our output voltage in this system as the voltage drop across our resistor R2. So this looks kind of similar-ish to some of the passive filters that we talked about in circuits 2. Okay. In circuits 2 specifically, we were looking at series RLC circuits and how we could use them as various types of filters, right? So you might recall when we took the voltage drop across a capacitor in a series RLC circuit, we had a low pass filter. When we took the voltage drop across the inductor in that series RLC circuit, we had a high pass filter. When we took it across a combination of the inductor and the capacitor, that was a band pass filter. And when we took it across the resistor, we had a band stop filter. So we just have some passive network here, and it will behave like some sort of a filter because the impedances of the inductance and the impedance of the capacitance are going to change as a function of our frequency S, okay? Now, looking at this thing, we can't really make an intuitive guess as to what type of filter it might behave like. And so that's where our transfer function is going to come in, and it's going to provide us some of that information. Okay. Now, one thing that I do want to point out, because our network is made entirely of passive components, so just resistors, capacitors, and inductors, there is effectively no way for this system to ever be unstable, okay? So we should always expect for our poles to wind up on the left-hand plane. The only time we should ever see poles on the right-hand plane would involve the use of active components, like transistors and things like that, that can boost signals and all of that kind of good stuff. And we're going to talk about, you can boost some things with passive components when you're operating at the resonant frequency, but that is something for about 2 weeks from now. Okay. So the first thing that I'm going to do is I'm going to convert this circuit from the time domain into the S domain, okay? And so that would simply be replacing my voltage source with its S domain equivalent, so just the Laplace transform of whatever our input signal happens to be. My resistors are going to stay resistors. My inductor is going to be replaced with an impedance of S times L. And my capacitance is going to be replaced with an impedance of 1 over SC. Like so. And then this is going to be my output voltage as a function of frequency. So since we have a voltage out over voltage in, this is representing a voltage transfer function. So what we're looking for is H of S is simply going to be the ratio of V out of S over V in of S. Now, this isn't too complicated to do directly, but we can break it down into smaller steps in order to make this more palatable. So what I'm going to do is I'm going to introduce an intermediate voltage, and I'm going to call that voltage V1 of S, like so. And I'm going to explain how I'm going to use this intermediate voltage V1 in order to figure out what my transfer function is. Okay. So V out over V in could be broken down into V out over V1 multiplied by V1 over V in. And the reason why I'm choosing to break it down in this particular way is because I think I can figure out V1 as a function of V in just by doing voltage division. And I know for sure I can find V out as a function of V1 by doing voltage division, right? So this is just a way for me to break it down into more bite-sized, manageable steps without getting lost in all of the details, okay? So let's start by finding V1 of S, okay? So V1 of S, using voltage division, is going to be V in multiplied by the following ratio, okay? So in my numerator, I should just have this impedance SL in parallel with this series combination of R2 plus 1 over SC. Okay. So that's going to look like SL times R2 plus 1 over SC divided by R2 plus SL plus 1 over SC. Okay. And then in my numerator, I'm going to have just that resistor R1 plus that exact same impedance for my denominator, because we're just applying good old meat and potatoes voltage division here, right? So that would be R1 plus, and then I'm just going to rewrite my numerator, R2 plus 1 over SC divided by R2 plus SL plus 1 over SC. So while there's technically nothing wrong with this, I personally don't like the fact that I have fractions inside of fractions inside of fractions. It's gross, and in this particular form, it is very difficult for me to tell what's going on in this system, okay? So we are going to make some simplifications to this thing. And I'll tell you that within a couple of algebraic steps, we will get rid of all of the fractions inside, and we will simply have a polynomial of S in the numerator and a polynomial of S in the denominator. So it's a pretty simplistic form that we could apply inverse Laplace transform techniques to if we were interested in how things are working in the time domain. But anyway, so the first thing that I'm going to do is I'm going to multiply this big behemoth by SC over SC divided by SC over SC. So this is me just clearing out all of those 1 over SCs to make this thing look less gross, okay? So let's do that down here. So when I take this SC of the numerator's numerator, and I multiply it by the numerator of the numerator on the left-hand side, what that's going to do is it's going to get rid of this 1 over SC right here. And so this term in parentheses is going to look like 1 plus S R2 times C. Are we okay with that? It's not going to multiply through by the SL because I'm taking care of that here. So multiplication of this times this whole thing is just going to give me SL times 1 plus SR2C in the numerator of my numerator. Are we okay with that? When I multiply this SC here through the denominator of my numerator, I'm going to wind up having an S squared LC plus SR2C plus 1. And when I multiply the R1 by SC over SC, it's just going to look like R1, so I'm going to leave that alone. And now I'm back to doing the exact same thing that I did in my numerator, so I'm just going to copy that stuff down again. Sorry, this should be an R1. Thank you. Okay. So what I can notice now, and I guess this was true in the previous step, it was just ugly, so I didn't like it, is that the denominator of my numerator is the same thing as the denominator of my denominator. So it would be really beneficial if I could make this R1 term have a factor of this in it as well, so that I could lump things together and get rid of all of my denominators. So that's exactly what I'm going to do. So all I'm doing is multiplying R1 by this denominator over this denominator so that I can lump those two terms together. Okay. So just to be clear here, I'm just going to multiply now by a factor of 1 in the numerator. And then I'm going to have a factor of s squared LC plus S R2 plus 1 actually, let me put the same thing up here. And so what that's going to give me is Vn of S multiplied by, so in my numerator, I'm just going to have SL times 1 plus S R2C. And then down here, I'm going to have R1 times S squared LC. Sorry, that should be a C, and that should be a C. Sorry about that. Like so. Are we okay with going from here to here? Anybody have any questions, comments, or concerns?
What I thought you were gonna do, I thought you were gonna make the, like, you were gonna just make R multiplied by, that was multiplied by the whole term, and then just be paid with it, that's pretty much what you do.
Yeah, and so I'm using this guy right here to get rid of this guy right here to get rid of that common denominator so that I only have a polynomial in the numerator and a polynomial in the denominator without fractions.
Yeah, it's simply.
And so what I'm going to do now is I'm just going to lump terms together. Okay. So let me take this one step further. So I'm going to leave my numerator alone. So SL times 1 plus S R2C is about as pretty as I can make that. So I can notice, let's start with the S squared terms, right? So I have an S squared times an LC times an R1. And then over here, I'm going to have an S times an S. So that's going to be an S squared, excuse me, an LC times an R2. So I could write this as S squared LC times R1 plus R2. Just to be clear here, I've taken care of this term and I've taken care of that term now. For just the S by itself, so S to the first order, I'm going to have S times R1 times R2 times C from this term right here. And then I'm going to have S times L from this term, or multiplied by 1 from this term right here. And so that's going to give me S times R1, R2, C plus L. So that's me taking care of this guy and this guy. And then the only thing that I have left is an R1. So I can very easily see now that V1 of S over Vn of S is simply that ratio. So let's do something similar to figure out what our transfer function V out over V1 is going to be. Okay. So V out, let me move this down a smidge, as a function of S is going to be equal to V1 as a function of S multiplied by, so let's just go back up to our circuit here. So I think this should just be R2 over this series impedance, right? So R2 over R2 plus 1 over SC. And let's multiply by SC over SC to get rid of the fraction in our denominator. And so this is going to leave me with an SR2C times a 1 plus SR2C. And from this, we can easily see then that V out of S over V1 of S. Oh, hold on. Let me scooch this thing over. I forgot to carry the V1 through. My apologies. Is nothing more than SR2C over 1 plus SR2C. Therefore, the H of S that we are looking for, so let me just scroll this really quickly. So I've got a factor of 1 plus SR2C in the numerator of this first transfer function. I have a factor of 1 plus SR2C in the denominator of the second transfer function. So when I multiply this guy by this guy, this part is going to cancel out this part. Okay. So that's just going to leave me with S squared times R2 LC divided by S squared LC times R1 plus R2 plus S R1 R2 C plus L plus R1, like so. So the last thing that I'm going to do here is I'm going to get rid of this coefficient that's multiplying the S squared term. So the reason why I'm doing that is because if we looked at our Laplace transform table, all of our S squared relationships and all of that kind of stuff, they have a coefficient of 1. So I'm just taking that to the outside so that we can make it look like things that we've seen before. And while I'm at it, I'm going to go ahead and just move this constant term of R2 over LC out as well. And so what that's going to look like is, actually, let me do it down here so that there's a little bit more space. So I'm going to have an R2 LC in the numerator divided by an LC times R1 plus R2 up here. So the LCs just cancel each other out for what it's worth. And then I would have S squared divided by S squared plus R1 R2C plus L over LC times R1 plus R2 times S plus R1 divided by LC times R1 plus R2, like so. Yes. Mhm. if I multiply it through, that's why I'm putting in the denominator of the second term and the denominator of the third term. Effectively, yes. So kind of similar to what I did up here for this R1, I multiplied it by this guy over this guy, just a factor of 1. And when I move the numerator part out, it's going to leave behind a denominator. Yep. So I have this thing, okay? So this is a generic form where I just have some constant value K, which in this case is representing R2 over R1 plus R2, times a numerator that is a polynomial in S divided by a denominator that is a polynomial of S. So let's talk a little bit about poles and zeros, okay? We talked about this the other day, but let's be a little bit more formal here, okay? So zeros are values of S such that our numerator polynomial n of S is equal to 0, okay? So since n of S in this case is equal to S squared, that means that we are going to have two zeros. So I'm going to call it omega Z1 and omega Z2. And both of these are going to be equal to 0. So the reason why I'm throwing an omega in here, kind of out of the blue, is because these represent the frequencies at which the output of our system is 0. Our poles are the values of S such that our denominator polynomial is equal to 0. So for our denominator polynomial, d of S, we have S squared plus R1 times R2 times C plus L divided by LC times R1 plus R2 times S plus factor of R1 over LC times R1 plus R2, okay? So our pole frequencies, omega P1 and omega P2, are whatever values of S will make this thing equal to 0. So this is a simple quadratic function, okay? So we can use our 4th grade, 8th grade, whatever the hell grade you learned quadratic formula in, and find that we're going to have a pole frequency omega P1 that is going to be equal to, let me scooch this down so that I have enough space. Negative R1, R2, C plus L over LC times R1 plus R2 plus the square root of R1, R2, C plus L over LC times R1 plus R2 quantity squared minus 4 R1 over LC R1 plus R2 All of this is over 2. And then our second pole frequency is the exact same thing, except that I'm going to replace this plus sign with a minus sign. Sorry. All over 2. Just to be clear, it's nothing more than the application of the quadratic equation. Okay, so our poles are well identified, our zeros are well identified. And so from this information, we could create a pole zero constellation to see whether or not this particular system is stable, right? So for what it's worth, so for R1 is equal to 200 ohms, R2 is equal to 100 ohms, L is equal to 10 millihenry, and C is equal to 0.5 millifarads. In this particular case, we find that omega Z1 is equal to omega Z2 is equal to 0. Omega P1 is equal to negative 20.040 radians per second, and omega P2 is equal to negative 6.653 times 10 to the 3 radians per second. So we would have a pole zero constellation. So this is our S plane, where this is the omega axis, and this is the sigma axis. We would have, let me do the zeros in blue. So I would put 2 zeros at the origin. They're stacked on top of each other, so we can't see the other one, but that's how we would represent a 0 on our pole zero constellation. And then we would have a pole here corresponding to negative 20.040 radians per second. And then we would have another pole out here at negative 6.653 times 10 to the 3 radians per second. So since all of our poles occur in the left-hand plane, this system is stable. If instead we change the value of our inductor, to 5 henries, while leaving literally everything else the same, our zeros would still be at 0. Omega P1 would be at negative 10 plus J 12.910 radians per second. And omega P2 would be at negative 10 minus J 12.910 radians per second, giving us a pole zero constellation that looks something like this. So once again, our zeros are at the origin, and then we would have a pole here and a pole here. where this represents positive 12.910. This is negative 12.910. And this distance out here is negative 10. So once again, a stable system, but in this particular case, now we've got complex conjugate poles. Okay, so we've gone through an example where we had numerous poles and zeros and all of that kind of good stuff. We've talked about now how to put our transfer function in a form that we can have a good idea of what our system's stability is. So now let's talk about, yes, Amir. That's sigma. Lowercase sigma. Sorry, I can't draw Greek letters for sure. So S, if you'll recall from when we first talked about the Laplace transform, has a real part, lowercase sigma, and an imaginary part, omega. So this is the real axis, this is the imaginary axis, just like we've always dealt with complex numbers. Okay, so when we're evaluating our system stability, let me scroll up here, we use the form K, so some constant, which could be 1, doesn't particularly matter, just some constant value. And then we had a polynomial in the numerator as a function of S and a polynomial in the denominator as a function of S. When we're trying to build frequency response plots, we actually need a slightly different form, okay? And I'll explain why in just a moment, okay? So for frequency response plots, we need our transfer function to be of a form, some constant K, and I'm just putting a prime designation here to let you guys know that this value of K might be different than this arbitrary constant K here. They could be the same thing, they might be different. So I just want to differentiate between them by putting that little symbol there, just so that you don't think, oh, I just leave that constant alone. That's not necessarily true. Yeah. So we have a different arbitrary constant K, and then we're going to have a numerator polynomial. But we are going to break it down such that we have 1 plus S divided by omega Z1 times 1 plus S divided by omega Z2 all the way out to 1 plus S divided by omega Z sub n if there are n zeros. And we're going to do our denominator in the same way. Okay? So 1 plus S divided by omega P1 times 1 plus S divided by omega P2 all the way out to 1 plus S divided by omega P sub n. So very similar form. We've still got a polynomial in S in our numerator and our polynomial in S in our denominator, but we have our polynomials broken down such that we can easily read off our poles and zeros from this. Okay? So this is bringing us into what are called Bode plots. Okay, and so Bode plots are what we had LT Spice do for us way back in circuits 2. Whenever we analyzed the frequency response of one of our filter networks, we had a graph where it was 20 times the logarithm of the magnitude of the transfer function on the y-axis, and it was the x-axis was our frequency, but it was a log plot, so we went from 10 to the 0 hertz, 10 to the 1 hertz, 10 to the 2 hertz, and so on and so forth. Okay. So let's introduce this really quickly here. So Bode, B-O-D-E plots, okay? So just for what it's worth, I'm just drawing a simple representation of a graph here. So on the y-axis, we have 20 times the log of the magnitude of h of s on the y-axis. And then on the x-axis, I'm going to put s comma omega, because for the most part, they mean the same thing here. We're looking at things only as a function of frequency, so we are making an assumption effectively at this point that the sigma doesn't matter. So that's why I'm allowed to use s and omega interchangeably, because I'm only interested in the frequency response or the oscillation part of our response. Okay. And then over here on this graph, just for the sake of argument, I might have like 10 to the minus 2, 10 to the minus 1, 10 to the 0, 10 to the 1, and so on and so forth. So I'm just showing you what the graph is supposed to look like. Okay. So let's investigate what Bode plots look like when we have poles and zeros at different places. Okay. So let's start by looking at a, zero at the origin. So for a 0 at the origin, no, I meant pole at the origin. Sorry, I'm getting myself confused. Pole at the origin first. We'll do 0 in a moment. So a pole at the origin effectively means that we would have a transfer function of the form 1 over s, right? Because if this is what my transfer function is, the value that makes my denominator equal to 0 is literally just s is equal to 0. So we all okay with that. Okay. So let's look at some things here really quickly. Okay. So we can never actually have a frequency of 0 on one of these plots. Okay. It does not exist. The number 0 does not exist on this axis. Okay. We can have 10 to the negative 90 hertz, so something incredibly close to DC, but we can never truly represent DC on these things. Okay. So what I like to do is I like to figure out what's happening at s is equal to 1 and then go from there. Okay, because that is something that exists. This 10 to the 0 represents an s is equal to 1. Okay. So at s is equal to 1, what would the value of our transfer function be? Let's look specifically at the magnitude here. Not a trick question. What? Absolutely right. So h of s in decibels is just going to be 20 log of the magnitude of h of s. So what's 20 log of 1? You guys have calculators, or you should be able to do this in your head pretty easily. Zero. Okay. So let's see something else. What if we let S be equal to 10? What would the magnitude of h of s be? 1/10. What would h of s be in decimal form? So what's 20 log of 1/10? Negative 20 dB. What about S is equal to 1/10? What would our transfer function's value be? Positive 10, right? And what would h of s in decibels be? Positive 20. So I'm going to write this as plus 20 dB. So I'm going to make a plot. I wish I brought a ruler here, but it'll be okay. So if we have a pole at the origin, then it will contribute or it'll have the following frequency response. So I'm going to put 10 to the 0 here in the middle. So this would be 10 to the minus 1. This would be 10 to the minus 2. This will be 10 to the positive 1. This will be 10 to the positive 2, and so on and so forth. So at s is equal to 1, it was 0 decibels. So let's make this part right here be 20, and this part right here be negative 20 dB. At S was equal to 10, or 10 to the 1, we had a value of negative 20 dB. So right here, and at S is equal to 1/10, or 10 to the negative 1, we had positive 20 dB. So effectively, what we see is a line that passes through the x-axis at S is equal to 10 to the 0, or 1, and it has a slope of negative 20 decibels per decade. So every pole at the origin is going to have this frequency response. So let's see if we can figure something out just knowing this, okay? So as a quick example, let's say that I have h of s is equal to 10 over s squared. So this is what my transfer function is. And can we use literally just this information to construct a Bode plot or a frequency response plot that is representative of this transfer function? So what I'm going to do is I'm going to break it down into, go away thing, 10 times 1 over s times 1 over s. Now, the reason why I'm doing it like this is because when I'm trying to find my frequency response plot, and sorry, I'm going to have effectively 20 log of h of s, which is going to look like 20 log of 10 plus 20 log of 1 over s plus 20 log of 1 over S. So effectively, I already know what this part looks like. It's this graph right here. So I would just have this plus another one of these plus whatever 20 log of 10 looks like. And I can add all of those responses together. And that would look like the total response of my circuit in the frequency domain, right? So multiplication here looks like addition with logarithms. So let me just put it down here. So this is the response of 10. Here's a response of 1 over S. And over here is another response of 1 over S. So I'm going to do this guy in red, this guy in green, this guy in blue, and then the total of them, I'll put it in purple. Okay. I'm going to give myself enough room here just to make this. All right, so here's S. So let's put 10 to the 0 here. So 10 to the minus 1 would go here, 10 to the minus 2, 10 to the positive 1, 10 to the positive 2. This is 0 dB. This is 20 dB, 40 dB, negative 20 dB, minus 40 dB. Okay. So let's do the red thing first. So what's 20 log of 10? Feel like we already figured that out, right? Positive 20. So the frequency response of that constant value is just a line at 20 decibels over all of our frequencies of interest. Okay. Our 1 over S curves or lines here, notice that's all that we have right here. So I'm going to have a line that has a slope of negative 20 decibels per decade, and it's going to pass through the x-axis at S is equal to 1 or 10 to the 0. Okay. So something like this. And then the blue curve is going to be the exact same thing. So I'm going to just try to draw that on top as close as I can while still making things relatively legible. And so to construct my frequency response graph for the total transfer function of 10 over S squared, I just need to add these things together. So I have a line with a slope of negative 20 decibels per decade added to a line with a slope of negative 20 decibels per decade. So that's going to look like a slope of negative 40 decibels per decade. And then I'm going to shift it up by 20 dB to take into account my constant factor of 10. So putting all of that together, it should pass this 20 dB line at 10 to the 0. So I'm just going to put a point there in purple. And then it should have a slope of negative 40 decibels per decade. So something like that. So the purple line would be my total frequency response. And I got that literally by just combining the frequency responses of the little parts that I broke it down into. Okay. All right, it is 12:08. I don't know that we have enough time to do another example here, so we'll start looking at a 0 at the origin when we get to class on Monday. Okay. That's correct. 1:30 in IESB 108. Thank you guys for your time. Hopefully this cleared up my shitty job the other day. We'll see.